All right, welcome. Today I'll be presenting the solution to another one of the challenges from BlueHat 2020, which was the partial impression or diplomatic door challenge. So my name is Alon. I'm an independent researcher and consultant. I've been working with Microsoft on BlueHat challenges for the past 2 years. And today I'll be presenting along with the highly esteemed Saar Amar from MSOC. And we'll be talking about the diplomatic door challenge. So the way this is going to go is that we're just going to overview the challenge and the general thought process behind it. Then we're going to take a look at the actual vulnerabilities and issues that you need to understand in order to solve it. And then we'll just show the actual solution. So those of you who have attended the conference know that the conference space was divided into 2 separate areas or states, which were divided by a central wall, and that central wall had a guarded door that you could access using the fingerprint reader. And this is just the general physical background that you need to understand in order to understand the challenge and what had to be accomplished here. Basically, this is a challenge where you have to attack some network entity, but eventually the goal is to bypass some sort of physical biometric mitigation here. So, except the actual physical presence of the door, you also, the second lead that you have is the code that we published on the day of the conference, which shows an application server written in Python and using Flask, which seems to be used to manage the fingerprint device in several ways. It provides information about the actual people who are subscribed to that fingerprint mechanism. There seems to be an option where you can download images of the fingerprints that are enrolled to the fingerprint reader. And most importantly, it defines, using information, using some sort of code configuration, it tells the fingerprint sensor which IDs of which users should be able to open the door. And taking a look at the code, you'll see a lot of very questionable looking decorators. Some make some sense in the context of what the server is supposed to do, such as decorators defining the mine types for certain routes. There's something that seems to implement some sort of access control on some of the endpoints. Something that supports range requests. I'm not exactly sure what that would be used for initially, and also batch routing. And the most important thing that you see is that while you can download images of fingerprints, basically of all users, in the current configuration of the server, you are unable to download privileged fingerprints. And when I say privileged, I mean fingerprints that are able to open the door. And again, you can see this in the code, since the IDs that are configured to enable opening the door are also excluded from being accessed in the fingerprint image route. So given all that information, we can try and raise some ideas on how you might be able to solve such a challenge. And given the interface between the code and the actual fingerprint reader, which is very, very small, it's unlikely that the attack is meant to be conducted on the actual fingerprint reader, but more likely there's more likely to be an issue with this huge meta programming nightmare in the form of all these decorators. And the general idea here is that you're supposed to bypass the access control decorator in some way so that you'll be able to get a picture of the privileged fingerprint. And one thing that I didn't mention earlier is that we had a 3D printing station that was also meant to be used in the context of the challenge, and you'll know exactly how momentarily. So let's talk about some of the issues that we see in the code. So taking a look at this decorator, the admin mode only decorator, which is supposed to implement access control over some of these routes, you can see that it wraps a certain function. And if admin mode is disabled, and you cannot, if element was disabled, you will not be able to use, you'll not be able to access fingerprints of privileged users or permitted users. Basically, or actually access any route that is related to these users. And as you can see, Admin mode is hard-coded disabled. So basically, any access that we try to perform on privileged users would be denied with the following message: admin mode is disabled. So this access control mechanism has one very glaring fault in that the action is first performed and only then the actual access criteria is tested. So this is a problem for so many reasons, but there's one major issue, an additional major issue with this server that, combined with this access control issue, provides us, it's a very lethal combination for the security of the server. And that second issue is that, and some of you found this issue just by fuzzing that Rangorator decorator. And as you can see here in this example, when you request a range that is malformed, meaning that the bytes parameter here doesn't really define an actual range of bytes and rather just has that separating dash value, you see that the server replies with a lot of binary data, which seems to change between requests, indicating that there is some sort of data leak here. And at this point, I will hand off to Saar, who will explain about this very interesting issue.
Hi, thanks so much, Alon, for this great introduction. My name is Saar, and I am a security researcher in the MSRCIL. Okay, so just like we saw, we need to find a way to leak the fingerprint image from the server. So let's start by trying to find some bugs. The problem is that after first glance of the challenge, we don't see any trivial vulnerabilities that come to mind. The challenge is written in Python, which is a memory-safe language. There aren't any classical Python issues here, no serialization, deserialization and stuff. And basically, it simply doesn't look like this kind of CTF challenge that hand out to you some vulnerability and expect you to exploit it. However, a few teams in the conference were able to play around with some HTTP requests, and they saw some really weird leak of uninitialized data. And it basically looks like this. If you try, just like we just saw, try to send this HTTP GET request, you'll see this blob of uninitialized data. Certainly looks like uninitialized data for me. And if you try to repeat this little experiment, you'll see that the data keep changing, and it contains many different kinds of data, which is pretty weird because we didn't see anything in the challenge that could explain such a behavior. Okay, in a moment like this, it's really important to keep in mind that what you see is less than what you actually get. Python uses its standard libraries, which in turn talks to the underlying operating system, CRT. And this is absolutely different kind of game, right? The CRT is huge. It's a wide attack surface. It implements many different kind of functionalities, such as file system, sockets, and etc. And for all of you who ruled out the CRT as a good candidate in this challenge, I just want to remind you here the 3 golden rules of life, which are clearly everything is vulnerable, everything is exploitable, and of course, POC or GTFO, because if we don't have POCs for the stuff that we find, they are basically meaningless, right? Okay, so let's go back in time, about 5 months or so, and try to remember this really important thread in Twitter. Here, I simply ask everybody, what is your favorite standard lib vulnerability? And I gave here a great example of a crazy wild copy, 64-bit, by the way, that was found in the standard library in Rust. Although this issue is very, very cool, what's even cooler is this response from Brandon Falk. Brandon tells us here about a super impressive and very, very elegant heap information disclosure vulnerability from the heap in the Windows CRT. And just like he says, it's effectively forever. Now, this is very good for us at this point, right? Because we see some weird behavior of some information disclosure vulnerability, which we can't quite explain, but we know that there was some very famous information disclosure vulnerability in the Windows CRT, and we know that there is a clear flow from Python into the Windows CRT. So this vulnerability could really connect some dots for us. So it looks like a very good idea to dig in here. So 5 years ago, Brandon reported this issue, super impressive heap information disclosure vulnerability in the Windows CRT. Just like he said, it was marked as a won't fix bug. Just to clarify here, guys, won't fix doesn't mean that a new version of the CRT is still vulnerable. It simply means that we didn't fix it down level, which means there wasn't any security update, security patch that fixed the older versions of the CRT. And with this new spirit, let's dig down and view the POC published by Brandon. What's really impressive about this POC, besides that it's pretty short, is that 70% of it just implement Hexdump. The actual POC is only those 3 lines of code. That's it. Very, very simple, very short, and very strong. What this POC actually does is try to open a file with WB+, which means that the file pointer that we will get will have both read and write permissions into the file. Afterwards, we'll try to write 1 single byte into the file, and then we will try to read 2 pages out of it. This is pretty weird because if the file doesn't exist, and in this case, the file indeed doesn't exist, we would expect from this fread call to actually return to us 0 bytes, right? Because there aren't any bytes to read. The problem is that it's not what quite happens in the older version of the Windows CRT. What actually happens is that when you call this fwrite call, this fwrite function, and you try to write some amount of bytes, you actually write it into the stdio's internal buffer as well. And once this happens, once some bytes are written into this internal buffer, even 1 single byte, the CRT marks this entire internal buffer as valid. Once this happens, there is nothing that stops you from calling fread and read arbitrary amounts of bytes from this internal buffer. And the bug here is that the CRT doesn't keep track of the amount of bytes that have been written. And it simply marks the entire buffer as valid, which is very, very wrong. And now, since this buffer has been allocated on the heap with size of exactly 1 page, this vulnerability summed up to be information disclosure vulnerability from the heap of up to FFF bytes. And indeed, if we will try to compile it again with the older version of the CRT and execute it, you will simply see that we have FFF bytes of uninitialized data, then 1 page of zeros because the buffer has been flashed. Okay, cool. So do you remember the third golden rule of life, which is POC or GTFO? So it's time to do some POCs. So we just saw the POC of Brandon, great POC, and I want to reproduce this POC in Python, specifically Python 2, because we see many hints around the challenge that it's been executed under Python 2, and there is a very good reason for that, which we will see in a couple of minutes. But before that, let's just see this very short POC in Python 2 again. This actually runs like under Linux because I want to show you that in a normal and correct behavior, the read call returns empty buffer, just like we would expect. Okay, now let's see what happens under Windows. So let's run Python 2, and define the following function that will actually trigger the bug. We know exactly what we need to do, right? We want to open some file. It's WB+. Okay. Now we want to write 1 single byte and then read FFF from the file. Let's close the file because we are human beings, and then return the data. Okay. Now, if we will call this function, we would expect to see FFF bytes of uninitialized memory from the heap. Fantastic. Okay, so the bug works. The vulnerability is triggerable from the context of Python 2 over Windows, which is great for us. But this is pretty useless at this point, right? Because we want to leak some data that we can actually use later in the exploit. We like usually want to leak pointers, metadata, port names, something that can be in hand in the rest of the exploits. So what we want to do here is to come up with some simple shape that will cause the allocation of the internal buffer in the CRT to reclaim some previously used allocation by us. So let's start by really simply just spray a bunch of strings, okay? And I choose that each of those strings will be a size of exactly 1 page, because the internal buffer size is 1 page, and I want both of the allocations to be serviced by the same user blocks in the LFH. So let's just spray, let's say 800x, okay? Now, if I will call the trigger of the vulnerability again, it won't do any good, because all of the allocations are still in use. And indeed, we see that we get uninitialized data from the heap, just like we would expect, but we want the internal buffer to reclaim one of the strings, right, to see that we can shape it. So let's try to free a bunch of strings. Let's say free every other allocation, okay? Great, so if I order 2, and let's set here empty strings, which will trigger the free in Python. And now we should see that the vulnerability could leak arbitrary bytes that we can control. Everything came from a previously used allocation by us, and this is very important here, because we can try to map the fingerprint image into the heap of the process, into the process address space, and then we will try to leak it, which is great. Okay. Now, I promised you that I will explain why we chose to use Python 2 and not Python 3. Python 2 still used the older version of the CRT, okay, as you can see here, while Python 3 uses the new version of the CRT, which is ucrt-based.dll. So the vulnerability simply doesn't exist under Python 3, so we simply can't use it here. Okay, cool. The problem is that once you go back to the challenge, you don't see the sequence of open, write, and then read. You will only see there open and then read. So yeah, this sequence doesn't exist explicitly, but it does exist implicitly. If you will try to consider the temp file.temporary file call, and you will do strace on it, you will see that it actually open the file, get the FD, and then write 4 bytes of BLAT into the file. Even if you will try to see it in Procmon over Windows, you will see the exact same behavior. The temp file or temporary file call in Python writes 4 bytes into the file, which is exactly what you need in order to mark the internal buffer in the CRT as valid, and then trigger the information disclosure vulnerability. And now with this shape and with this POC, we can go back to Alon to see how we will finally solve this entire challenge. So back to you, Alon.
All right, thank you very much, Saar. So a very interesting vulnerability that I'm going to talk about how we can utilize it in the context of this challenge. So as you recall, we have a lot of these weird-looking decorators, and the previous issue that we discussed before this one was the fact that the admin mode or the access check mechanism here first performs an action and only then verifies if it's actually privileged or not before returning the error. And what this means for us is that the leak here is applicable in that we can read the privileged fingerprint image from the disk. It won't be returned to us from the route that we're accessing, but it is being read to memory. It gets converted into a temporary file by the result2fb decorator. And then the Rangorator decorator is used to implement ranging over that file pointer. And of course, all this happens before the access check is actually performed. And what we can do in a very similar way to what Saar demonstrated, and by shaping the heap, we can try and prime our heap with just under 44 page size byte slices of our image, and then just leak it part by part until we have the full bitmap. And in the beginning, I talked about another interesting feature of the server, which is called batch requests. And the reason we included this mechanism, which what it does is basically just allow you to, instead of issuing a lot of connections to the server and having it process each request separately, you can basically just take all the requests, batch them into one single request, which is issued over a single connection, and then the server will perform that all of these actions, all these batch actions in a single flow, one after the other, and return the result to you. And this works by just using the Flask batching client. So you can actually solve this challenge without using batch requests, but we added it to, we thought that there may be issues with several people attacking the server at once, which could disturb the heap shaping process for each single user. So that's the reason why that was there. And in the snippet that we have here, you can see that we do use it. But once again, it was eventually it was not 100% necessary to actually solve the challenge. So back to the actual leak. How do we accomplish priming the heap and then leaking parts of the image? What we do is basically just issue several requests to that restricted route, which you can see inside of the batching context here. We basically just issue spray count, which in this case is 10 requests to that fingerprint. Each one of these requests will just return with the admin mode is disabled message, but it will have primed our memory with the relevant part of the image. And once the memory has been primed, we issue another request to the enroll page, and we use that malformed range header in order to trigger our leak. And the reason why we do this on the enroll route is because it basically just returns the shortest message, which just allows us to leak more bytes in a row. And we return the content of that leak. And what you'll see here is that you need to play around with the parameters a little bit, and sometimes you won't get the image in the correct order, or you'll have some additional data. But once you do it enough times and you mess around with the leaking code, you will eventually start getting clearer and clearer images of the fingerprint. You can also, this is a very rudimentary example of how to perform the leak. You can write much more sophisticated code to match the ends of the buffer together to make sure that you get reliable data. But the point here is that it is possible to leak the entire bitmap of the fingerprint. This is actually my fingerprint, which can open the door. And once you have that bitmap, comes the actual physical part of the challenge. You need to take it, you need to extrude it, so it's in a 3D form. And then you would go to our 3D printing station and print an image, a resin model of the fingerprint, which you can then use to open the door. And here you have just a keychain that we printed out in the end. As you can see, it has the contours of that fingerprint on it, and it is able to open the door. And that is it. So thank you very much for watching. Thank you, Saar, for your explanation on this very interesting vulnerability. And we'll see you next year. Thank you so much.